All right, welcome everybody. This is the member due segment tonight. We have with us Captain Michael Seis, who is an F-35 pilot, and he's going to tell us a little bit about what his job entails as a fighter pilot. Go ahead, Mike.
Hey there. So I put together a small presentation about what fighter pilots do and how we apply aerospace science in order to make sure that we win and stay alive. So I'll turn on the screen share here and start that.
Did he say win and stay alive?
Those are both very important things, Jake.
Yes, I guess so.
So Midnight Dogfight, how fighter pilots apply aerospace science. Go ahead and stop me anytime if you have questions, and we can go ahead and dive a little bit deeper. So I want you to think about a scenario where two fighter aircraft are approaching head-on, and they both visually identify each other as an adversary. And when this happens, we pass only a few hundred feet away in training and potentially in real life. So I guess the question that I want you to think about as I go through this is, which direction do I turn in order to win? And the answer is it depends, and we'll get into why and how we get to a decision. So a little bit of background first. What is a dogfight? So a dogfight between two planes is really just turning. But our basic air-to-air weapons require us to point at the other aircraft in order to employ the weapons and shoot. And what this means is, if one plane is able to shoot first, then he's going to survive and win. And you don't want to be the guy that doesn't shoot first. So when we think about a dogfight and turning, there are two types of maneuvering that are important. And one of them is the maximum performance in maneuvering the aircraft at its limits. It can't go any faster. It can't turn any harder. And there's also sustained performance, and that's how the aircraft performs over time.
This is scary.
No. So we won't get into the math too much because that would take quite a while to explain. I'm sure Nick could do a much better job than I possibly could anyway.
Probably a couple of degrees if you really, really want to understand it.
Yeah. So it doesn't take a degree to fly a fighter other than to get a bachelor's, but yeah, I have a few friends that got theirs in music, so and they're still flying with me. Anyway, there are two types of limits that we care about when we turn, and that's the lift limit and the G limit. And the lift limit, you can think about it, when the plane gets too slow, there's only so much air that's passing over the wings, and the pilot can only make the plane turn so hard before the wings stop producing lift. And if the pilot tries to turn too hard, then the plane's going to stall, which means it's going to stop flying. You don't want to stop flying during a dogfight. That's bad. The second limit is the G limit. So if the airplane is fast enough, the pilot can turn plenty. The wings aren't the problem. It's the structure of the aircraft that can only withstand so much turning. So if the pilot tries to turn too hard, then the plane's going to break apart, which also means he stops flying. There's also the speed limit, and every aircraft has one, but we're not going to talk about it since it really only matters in a straight line. And for fighter aircraft, they don't get up near their speed limit in a dogfight. So if you put these on a graph and you make the x-axis the speed, how fast the aircraft is going, and you make the y-axis its turn rate, and you can assign whatever unit you want to that, degrees per second is most common, then this is what the diagram looks like, and it's called an energy maneuverability diagram. You see on the left side is the lift limit. When the aircraft is going slow, it can't turn faster than its lift limit, and there's a corner there that's called corner velocity, and above that is the G limit, and that's the structural limit of the aircraft at that speed. And whenever you make these charts, some assumptions that apply are that it only works at one altitude, and it only works at one weight. And airplanes get lighter as they burn gas, so this is really just a snapshot in time. But we can use this to try to figure out what we need to do in a dogfight. One more important thing about the graph is that turn radius is here as well. So the green line on the left shows the minimum turn radius of the aircraft, and the slope of the graph from whatever point you pick to the origin is equal to the turn radius, and that gets important a little bit later. We'll get into that. The math, though, is pretty interesting. So the slope of this graph is equal to turn rate over speed, and it follows that turn rate is the amount of turn over time. Speed is, of course, distance over time. But if you take the turn rate divided by the speed, then what you get is turn over distance. So you can think about it in terms of a greater slope is more turn over the same distance. And I've kind of illustrated that in the lower left corner here. So you see the blue circle is more turn in the same amount of distance than the red circle. And then I've unhidden those circles, and you can see that the blue circle is significantly smaller than the red circle and has a much smaller turn radius. So the greater the slope from the point that you pick on the graph to the origin means that there's going to be a smaller turn radius.
I noticed that. So Michael, Captain, that little graph in the corner there, it's kind of like saying it's easier to turn with a skinny lady than a bigger lady.
That's one way of thinking about it. and bigger aircraft have a harder time turning as well.
Yeah, I got you. Amazing.
There's also a really interesting relationship between like the stability of an aircraft and how maneuverable it is too. So if you have a very stable aircraft, which tend to be the bigger aircraft, they have a harder time being excessively maneuverable. And that's part of the things that makes fighter aircraft so good, is that they tend to be kind of an unstable plane and difficult to fly. But the advantage that you get out of that is they're highly, highly, highly maneuverable if you can control them.
Yeah, we could talk about that for a second. So from my experience in the F-16 is, as you know, Nick, an aircraft with relaxed static stability, what that means is it needs a computer in order to stay airborne. I, as the pilot, cannot input I can't make control inputs fast enough in order to keep the system stable. So if I was controlling, then the aircraft would pitch up and it would just go out of control. But with the computer, controlling what is naturally a slightly unstable system, it means the aircraft can turn and roll much faster than anything else out there.
Yeah, absolutely. The addition of a computer into the system allows you to do way crazier things than you would ever be able to do if you were in complete control of the aircraft. And so many modern fighter aircraft today, when you give an input in the stick or in any kind of the control surfaces, the computer is interpreting your input and just modifying how it controls the plane to make the plane go in the direction that you're pointing it, as opposed to a more traditional aircraft where the stick is actually physically connected to the control surfaces, and when you move your stick around, you're moving the control surfaces in turn. So it's really interesting to see what we can do with fighter aircraft today.
Yeah, and all the pilots joke about how we only get a vote. The computer decides.
Exactly.
So the last part of our performance piece here is sustained performance, and you can think of it as two things really affect how fast a plane turns, and that is how fast it's going and how much the pilot wants to turn up to the lift or the G limits. But over time, a plane is going to slow down if it is turning at a faster turn rate than its sustained rate curve, which I've got displayed there as the blue line. And then the maximum Y value on the graph, the maximum sustained turn rate, is an important piece as well, because that's the fastest that the aircraft can turn without slowing down and moving further to the left side of the graph. So.
And you say the computer would monitor that for you as you're flying?
Well, it does to a certain extent. In a more modern aircraft like the F-35, I have displayed to me a caret that tells me whether or not I'm slowing down or speeding up, which other aircraft don't have. You have to notice the airspeed moving up or moving down, but being able to make faster decisions is important. So it's nice that the computer knows that and can calculate it based on my weight and airspeed and how much of the throttle I'm using, whether or not I'm in afterburner, that sort of thing.
How much freedom does the computer give you in terms of moving around? And
Sorry, I can't hear you very well.
How much freedom does the computer give you in terms of maneuvering?
So in more modern fighter aircraft, starting with the F-16 and all the way now to the F-35, there's an AOA limit. It's called angle of attack limiter. And it will only let me pull so much, because if I pulled more than that, then the aircraft would go out of control, as we discussed earlier. Also, with the F-16 and the F-35, there's a G limiter, so I can't break the aircraft and pull above the G limit. With other planes, World War II, it began to happen as fighter pilots began entering dogfights and going too fast. They could pull too hard and actually break their aircraft, but modern computers.
That's crazy, isn't it?
And that's also another interesting thing too, as far as when it comes to warfare. Getting into a dogfight and having your airplane no longer be usable after the fight because you've over-G'd the aircraft and now the wings are broken is almost as bad as losing the plane itself, because then you can't fight with it anymore because the plane is broken. So that's part of the reason why making sure you don't break the plane is also a consideration when entering a dogfight like this.
I would sure be on the store side of maintenance anyway. I have been a couple times already.
Captain over G, eh?
What is the G limit on an F-35?
So the nominal G limit is 9. It's a little bit lower than that when it's heavy with full of gas. Most fighters today have a 9 G limit, and some would argue that that's there not to protect the structure of the aircraft, which, I mean, most of them are the same, and it's close to 9 Gs, and there's a factor of safety engineering-wise in there. But the real limit these days is the pilot, and we can only withstand so much and require special training in order to withstand higher G forces for sustained periods of time.
There's also, I mean, from a perspective of an engineer, why design a structure that a pilot will never be able to fly, right? So if you design an airplane that can handle 11 Gs, 12 Gs, 15 Gs, 20 Gs, but a human operator can only ever handle just over 9 Gs for a few seconds or something like that, then why design a plane that can do that if nobody can ever fly it there is a common question in engineering. And especially with aircraft, usually when you add structural strength, you're adding weight to the aircraft. And when you add weight, you're lowering the performance in almost every characteristic. So aircraft engineering especially is this really delicate balance of making the plane just strong enough to handle the things that it's supposed to do so that you can get the most performance out of it, because usually that's what you're chasing, is the performance aspect.
Awesome. Well, let's see what else. When we put the performance aspects of the planes, or maximum performance and sustained performance together, then we get what's called the flight envelope. And there are different graphs and different styles of graphs displaying a flight envelope, but this is the one that fighter pilots care about. So we've got the lift limit on the left, again, the G limit in the upper right, and then the sustained performance curve there on the bottom. But this only shows my plane, and I need to know what my opponents look like. And we can gather that based off of known test data or our engineers' best guesses at an aircraft's performance based on how it looks. And a lot of calculations can be made that way. So I've made a notional diagram here with an adversary aircraft, and you can see that they're different. And we're going to explore 2 different types of advantages that pilots care about in a dogfight when they compare these diagrams. And the first one is a radius advantage. So if one plane turns left at the merge and another plane turns right, so this is a top-down view, then you can see that the plane with the smaller turn radius wins. And even if that red plane had turned less and it had a less turn rate, because it has a smaller turn radius, it's going to end up pointing at the blue fighter first.
Ooh.
So we've discussed that pointing first means that you win. The second type of advantage is a rate advantage. So when both planes turn the same direction at the merge, so one plane turns left and the other one turns left, or right and right, then you end up with what's called a two-circle fight. And in this case, it's the plane that can turn the fastest that wins. But remember, we talked about if you pull above the sustained rate curve, then you slow down and your turn rate slows down as well. So pilots have to fly at that sustained rate curve, and it takes quite a bit of discipline to not pull too hard in order to try to point first, but you end up slowing down and losing. So you can see here that the blue fighter has a better sustained rate and ends up pointing at the red fighter first. Any questions on that?
Well, how you only have a short time to shoot, don't you, before you go on by? Is that right? When you're circling like that?
That's true. And very generally, you only have what's called you have a brief moment in time where you have a WEZ, is what we call it, a weapons employment zone. And with our basic air-to-air weaponry, then there's a maximum and a minimum range. And when you're dogfighting, if you get too close, then you can't employ your weapons because they're unable to turn in that short distance as they're accelerating with their rocket motor for a missile. And then you don't want to shoot someone too close with the gun because that would be bad for you as well.
Yeah.
So if we look back at the diagrams and put them together, I've highlighted a couple areas where the red plane has a radius advantage in the light red there, and you can see that I've drawn a couple lines from the lift limit of the blue fighter and the red fighter to the origin. You can see the red fighter has a greater slope, so it has a smaller turn radius at its lift limit. But you can see that the blue fighter has a greater sustained rate than the red fighter. So the blue fighter is going to have a better sustained rate and is going to have that advantage. So going back to the beginning of my slideshow here, at the merge, which direction do I turn? Do I turn left or do I turn right? And this is the answer. I want to force geometry to look like this. If I'm in the blue plane, I want to fly a two-circle fight, meaning I want to exploit my rate advantage. I want to turn in the same direction as the other fighter, meaning if he turns, in this case, left, then I also want to turn left to force that geometry. But if I'm in the red aircraft, and this is all a top-down view again, I've got a radius advantage. So I want to turn opposite. And that might mean reversing my turn. If we're both in a left-hand turn at the merge, I'll reverse my turn to force a one-circle fight geometry that you see there, the lower portion. Both of these cases allow me to point my aircraft first, and both of them require prior study for fighter pilots to know. So what we do is we take the graphs of our planes and we take the graphs of other potential adversary aircraft and what we think that they can do based on how that plane looks and other things that we might know about it. And we decide before we ever get to the merge that if I merge with that type of plane today, then I'm going to force a two-circle fight or a one-circle fight. And that's how we train in order to keep ourselves alive.
Holy mackerel.
So
I have no idea.
What are the strategies for forcing a certain type of maneuver? I mean, to me, the first thing that comes to mind is see which way they turn, kind of like a game of chicken, see which way they go, and then based on which direction they go, counter with the best possible move that you can make.
Mm-hmm. That's pretty much it. And it's happened where I've merged in training with another aircraft, and I wanted to force a certain type of fight. In this instance, I wanted to force a two-circle fight, and my adversary tried to reverse his turn in order to make it one circle. Well, I just reversed my turn again. It's sort of a battle of wills at that point. Sometimes certain situations can force you into making one decision over another. You can't, for example, force a one circle fight, and I can't draw to display this perfectly, but if you got too much distance between you and the fighter that you're merging with, then if you turn away from him, he's just going to turn towards you, and you're giving up what we call turning room. So even though you might have a smaller turn radius, if we move that red line significantly up, then it would be neutral with the blue fighter, or the blue fighter would be pointing first, even though they've got a radius disadvantage. So knowing the exact numbers, my exact turn radius, and knowing how close I am when I'm merging based off whatever my radar is telling me, or just my eyeballs and how I've attuned my vision to tell me how close I am to other aircraft, is very important in making those split-second decisions in order to make the right decision. Likewise,
it seems like both of these, very basic scenarios show almost a head-on confrontation. And what you're describing is a situation where instead of both planes coming straight at each other, they're kind of offset a little bit.
Exactly, they're offset. So it doesn't make sense for me to turn this direction.
Yeah,
if I'm going to go that direction. So I have to force that merge to be closer, and then I can use my radius advantage. Mm-hmm. The other situation is, this all assumes that we meet at roughly the same airspeed. If I am already slow, maybe because I've threat reacted to a missile that my adversary shot at me from several miles away, a radar guided missile, and I did a barrel roll around it, and now I'm slow. It doesn't make sense for me to even try a sustained rate game plan, because I can't speed up fast enough to use my rate advantage. So I'm going to do the best that I can in a one circle fight using whatever is the best radius that I can generate. And at that point, it's pilot versus pilot, not necessarily plane versus plane. So I'm going to make it as difficult of a problem for my adversary to solve as possible in order to ensure my own survival. And if I can keep the fight neutral, even if I start out at a disadvantage, then I should have a friend who's flying with me, who should be there sooner rather than later to take care of my adversary.
Yeah. So much of, in my experience, so much of this strategy is based around not only developing weapon systems that make it so that you don't even have to enter into a dogfight in the first place, because you can take care of somebody from so far away they don't know you're coming. Mm-hmm. Or the alternative is that we try to develop strategies around having extra people with you at all times, and that's what your wingman is for, and other similar scenarios where it never has to come down to, can I turn faster than the other guy, if it doesn't have to. We try to avoid, through strategy and engineering, getting to this point at any point in time. But when you do get to it, it's really smart to know who can turn faster than the other guy.
Absolutely. And you won't find a fighter pilot alive that doesn't train to BFM, because it is what we call basic fighter maneuvers, is dogfighting. Because we recognize that it's a contingency, but it's something that's very possible, especially as the fog of war and more complex scenarios evolve, and there are lots of aircraft in the sky. Makes it more likely that you're going to end up at the merge. Also, dogfighting is pretty fun. It's
good night. Did you really? He's not only crazy for flying that plane. Now he thinks it's fun. I'm so proud of you. That's amazing.
Thanks. Appreciate it.
Dogfighting is fun. Yeah. Okay. You got to get a tattoo.
A tattoo?
Yeah. Dogfighting is fun.
That's my quote line.
Say, listen, when I see a movie once in a while, and there's a dogfighter, and somebody screams, "You're out of the envelope." Is that what they're talking about?
They say that you're pushing the envelope.
You're pushing.
Which sometimes can mean that you're about to break yourself.
Is that what it means? Okay.
Or a metaphor.
Now, is there an alarm that goes off just before you break the plane in half?
In some planes, the ones that don't have limiters, like the T-38 is a trainer that we use for intro to fighter fundamentals, has a beeper. And as you get closer and closer to the G limit, the rate that the beeper goes off in your helmet gets faster until you get to a solid tone, which means you're within 0.1 G of the G limit. And then after that, it'll do this boop, 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 boop over G, which is a sound that I've heard. which means I got to practice that flight again.
And also a situation where you bring it back to the guy who has to maintain and fix the airplane, and he's very, very mad at you when you bring it back.
Bring it back.
That's true.
Sweet. But Captain Seis, I don't know what else to say. Is we have one little. Well, there's no way we can thank you for your service.
Oh, I appreciate your support. That's all I need.
Not only is he a brave man, you see, talking about taking out his opponent and the guy shooting at him, and he's all that. The math, the punishing amount of math that you had to study.
We stand on the shoulders of giants, and you know, I'm sure you're aware of how science has evolved, and everyone's just built on each other's work. And I think one of the important things that maybe your audience behind you there needs to know is it's not all theoretical, and at the end of the day, there are a number of career fields out there that require you to apply the math and the science that you know. I did not realize it would be quite as intense as it ended up being, and that it's really rewarding to be able to apply it.
They ought to have some sort of math alarm on the airplane. You know, there's too much math here. Something like, hey, Jacob, could you take a picture of the sign over the window up there? Can you get that on the camera? There's something that these guys sitting by me might not know, or Colin, or people who are watching might not know. We're going to put some up here on the screen, which you might have seen. Looky there. Does that mean anything to you, Captain Seis?
Oh, it does. Yeah, that's the best high school in the world.
Yeah, it is.
Did you go to that high school?
Yeah, sure did.
You guys go to East High School? That's what we all have in common. I graduated from East High School, and all these guys went to East High School. And there's a guy that knows what 7 times 8 is.
Yeah,
Barely.
Colin, did you go to East High School?
Yeah, I used to before I graduated, but.
Oh, yeah, okay. That's what I figured. So the only outcast person we have here is who?
Yeah.
Jacob over here. That's right. Well, I hope someday that you're a successful ace. Well, you're already a successful ace. You really are.
Not by the classic definition, but I appreciate it.
If you can do that math, you deserve to be an ace. Good night.
I think Nick's done way harder math than I have.
Yeah, but I don't get to sit in a cool airplane.
That's maybe true.
So what's your next flight? We'll let you go.
So my next flight is tomorrow morning, and I'm going to be practicing close air support out on the range here in Utah.
Okay.
So,
you get to shoot your guns?
Nope. Well, maybe. The weather would probably prevent that. You don't want to shoot the gun at the ground while you're in a cloud. Don't know who you're shooting
You can't
at.
see what you're shooting at. And usually it's important to know what you're shooting at.
I got to know what you're shooting at. Well, great. But let's let the man go to bed. He's got to get up early in the morning and go fly his plane.
Captain Seis, if you had to give one piece of advice to a young person who, you know, was trying to figure out what they wanted to study, or maybe they wanted to do what you do, what piece of advice would you give them?
I would encourage them to open their minds about what they're studying, and not just realize that the subject itself is important, and they all are, especially as you delve into more theory and try to push the boundaries of human knowledge. But in many careers, there is a significant opportunity to apply the science that has already been built. And I would say my career definitely does that, and there are others out there. So don't limit yourself based off of what subjects interest you. If you can find something and a passion that, I guess, words are hard. You can find a passion that is going to be something that you can apply: math, science, engineering, all of those things.
You know, I tell a lot of people that I know I'm an engineer, but that doesn't necessarily mean I was that great at math. Really, it was being able to understand that you can do a lot with math if you're willing to see what you can do with it. And sometimes it might not feel like what you're learning at any one given time has that real practical application. But if you can find that practical application, you can do amazing things with it, like fly a fighter jet if you wanted to.
I think that's a much better way of summarizing what I was trying to say.
Hey, we got to let you go, Captain Seis. But am I daydreaming? Did I go to an East High football game and the center snapped the ball over the quarterback's head?
That may have happened more than once.
Were you a center on East High football team?
Mm-hmm.
Were you? Yeah, okay. I remember that night. What? You're a center on an East High football team?
Used to be.
Yeah. See, we got it going here.
Yeah.
From East High.
You're definitely better than I was.
And see, he hiked the ball over the guy's head, but they're letting him fly a $100 million jet.
I have hope yet.
You have hope. There you go. All right, we'll say goodbye. Everybody say goodbye.
All right. Bye, guys. Nice chatting with you. Nice to meet you, Nick. Good talking with you, Colin.
Thanks for your time.